still good morning. My name is Masanori Shukuya from Tokyo State University, and I'm very happy to be here, to be able to give a talk to all of you. My connection with ECAT is going back to, I don't know, maybe 3 years ago. My friend working as chief officer in the Icelandic Energy Agency, who used to work as a professor at the KTH, Stockholm in Sweden. He is one of my old friends, and he just happened, ECAT, just happened to meet him when he has a visit. He had a visit in Iceland, and that professor, old professor at KTH, told him about me. And then he visited our campus, because our campus was now quite old, but still newer than this campus. And we had a little bit better thermal insulation of the whole buildings in the campus, so that that idea may be applied to the buildings here in the campus. So he visited us, and he gave me a chance to give a talk to some other people 2 years ago? Yes. So this is the second time for me to come over here to meet new people here. As he introduced you, I have been involved in the thermodynamic research in relation to the built environment. And this is quite, I think, a hot topics, but it's very much related to the hardcore physics, I think, in the field of thermodynamics. So it must be very difficult to grasp the whole idea within 1 hour or so. So I'd like to introduce you what kind of knowledge that we can get from that kind of concepts in use for describing environmental space and environmental design and so on. And 1 week ago, you made an introductory explanation on a variety of thermodynamic concepts.
Yeah, with the aim to
Okay. So are you all in the field of natural science, or maybe some others are in rather social science oriented? Could you raise your hand? Natural science? So half of them. So the rest of you are in the social science oriented. Am I right? Okay. So anyway, what I would like to do today is that not the very specific natural science oriented things, because we all have a variety of people here. But still, I like to have some very deep core scientific concept in explaining what I have been doing, and I hope all of you may show some interest. Okay. So I have been, as I already told you, I have been involved in this field of thermodynamics and building science. And also, some of you may feel this room very warm, or maybe just good, neither warm nor cool. So could you, again, raise your hand? Who feel very hot, this room? So 1/3.
not very hot.
Not very, but rather a little bit hot. Okay, neither warm nor cool, just neutral. Okay. Who feel cool or cold? Nobody. Okay, that's good. So in winter time, we need to heat these rooms to be able to feel neither hot nor cool. but in this room, we feel a little bit hot, okay? So first of all, I'd like to share with you which temperature this room is, okay? So I'd like you to guess. I'll give you some Okay, so you can guess which temperature it would be here in this room. Later, we can measure the temperature here. So just guess. It's okay to make a mistake, okay? Please raise your hand, those who imagine the temperature is lower than 80 or equal 80. Okay, nobody. So in this range, one, well, just be confident. Two, are you? No? This range. It's okay. So again, those who imagine this range. One, two, okay. This range. Three of you. This range. 5, 6, 7, 8, 9, 10. Okay. I made a mistake. This range. 1. This range. 0 and over 28. Okay, wow. So my guess is okay. So let me measure. This is the very simple infrared thermometer. So this measures the surface temperature. If you put like this, we can know of the ceiling temperature, okay? Because infrared radiation comes off from the surface, and it can measure the surface temperature, okay? So let me do it. The result is 23.7 degrees. Okay, quite high, I think. And the floor surface, well, it is quite surprising. Okay, and the window. This is the heater. Okay. So this is so we can know that there are quite a variety of temperature. This is not uniform, okay? And also we wear different clothes. So if you just leave your jacket, and then you may feel a little bit cooler than before. So all those things affect the thermal perception, okay? And I'm now standing and talking to you, and you are sitting and very calm. So my metabolism, thermal energy emission is probably larger than you. So I feel a quite hot. I'm now a little bit sweating. So I feel very, well, maybe personally, I wonder whether this is right or this is right. But I assume that this is winter and today is cold, so that I put my one here. But anyway, the average would be 22 degrees C or something. And this is the thermometer that we can measure the surface temperature, not the air temperature. So air temperature might be much higher than this temperature, because the heat is going out from this room through ceiling, windows, walls, and probably floor surface. I don't know why this is so low. Maybe downstairs? No heating. But there is room. Oh, okay. So probably the downstairs here is the room, and the temperature is quite low. Maybe 10 degrees C or maybe 12 or something. Maybe lower. So much heat is lost in this way, so that the surface temperature becomes something like this. Okay? So all those things affect our sensation, our thermal perception, and so on. So definitely we need heating. But the heating, usually we assume that such equipment will do. Okay? This is the things that everybody believe, except us. My definition, I will show you later, but heating can be made by such equipment, but also by windows, walls, and so on. Why? Because we emit a lot of heat from our body. And how much we emit the heat, I will show you later with some very simple question to you. Okay? So let me come to the slides, and let me explain a little bit about what I have been doing and what is the Xsg concept. Okay, so here you may have not yet heard this terminology, bioclimatology. Climatology is the science on the outdoor climate, global climate, and also local climate, but also indoor climate. Okay? The temperature inside the room may change from maybe 15 degrees C up to 30 degrees C, depending on the weather condition, depending on how we use the buildings and so on. So we have the indoor climate. So we need to control the indoor climate so that we can enjoy the healthy condition and comfort. Otherwise, you cannot concentrate on the lecture or some exercise and so on in this room, or maybe in your room, in your house, or some other places. And it is very important to have the nice indoor climate. So such a climatology is what I have been measuring. And why it is bio? Because it is all related to human body. Okay? So we need to know some aspect of the human anatomy and also human physiology in relation to the indoor environment and also outdoor environment. Outdoor environment is under the effect of the solar radiation, wind, clouds, and so on. Okay? So why indoor environment is important? This is because the indoor environment is our closest environmental space. Over the last 20 years or something, many people discuss about the global environmental degradation, but it is also, I think the discussion should include the indoor environment, because indoor environment is related to the global environment. And we spend 80 or 90% of hours each day indoors. So let us assume that our lifespan, 80 years, as I mentioned in the poster. So we spend our life more than 70 years indoors. So it's very long, right? So it's very important. Though many, many people disregard that is important. So that is a big problem. That's why many, at least here in Japan, many, many buildings still have very, very poor condition of thermal insulation. So that they tend to use very powerful air conditioning unit, very powerful boiler, that kind of things, and also the much electricity to have indoor climate, not only in winter but also summer. And such electricity and gas come from the geological resources and also nuclear and so on. And what happened 3 years ago, you all know. So it is very important to have a rational technology, rational indoor climate with rational technology based on the rational science. And to do so, Exergy concept is one of the key concepts, I think. Okay? So this drawing that you saw in your poster is, if I'm asked what your image over the last 20 years of my research and education, this is it. So as I explained, we spend long hours of time every day within the built environment, and all of them, not all, but almost all of them live in the urban environment, and urban environment such as Musashi, Sakae, Tokyo, and so on, where I'm living in Yokohama, all those areas are surrounded by regional environment, and the biggest regional environment is the global environment. So we call such a relationship nested structure. So one of the problems that we are facing, the global called global environmental problem, is this nested structure work not in harmony with each other. That is the problem. So it is very important to know how the global environment works, how the human body works, and how built environment together with the urban environment should be designed. So at least with respect to the technology to have the indoor climate, there are two kinds of technology. You may not have heard these technical terms before. One is passive technology, and the other active technology. We have had very, very long history of the human being, at least 30,000 years or something, and long ago, we didn't have any fossil fuel and so on, just use the fire from the wood and so on. So those days, they were in a kind of very, very smart idea, having these small windows with white painting in the areas of a lot of sunshine, dry climate, and so on. And we can see some beauty in the island in Greece or Turkey or somewhere like that. And also, we can see this kind of building structure. This is an example in Japan, thatched roof, very thick, 60 centimeter thick or something. And all of you know, as you know, in summertime, we have a lot of green. So it is a good idea to use this kind of material. at the roofing. And 60 centimeter thick is a very, very nice thermal insulation, so that the surface temperature inside such roof is usually maintained around 27 degrees C or 28 degrees C during summertime without any air conditioning unit. Why? Because sun control with this keeps the soil surface temperature under the roof. The soil has a very, very big capacity of the storage of thermal energy, so it is very, very stable. So it becomes usually 27 degrees C, 28 degrees C surface temperature. So if you have very thick thermal insulation, we can maintain the surface temperature around 28 degrees C or something without anything at all else. So that is a very, very smart idea in those days. And active technology. This is the technology that came up with the human ideas over the last 100 years or something. So electric lighting, electric heating, electric cooling, that all those things. Of course, it is a smart idea, and without such idea, we cannot use computers, slide projectors, the video camera, and so on. So it's, again, very important. But the problem is that we rely too much on active technology, disregarding the passive technology. That is the problem. And that may have caused some problem in the human health and human discomfort also. So we need to solve that kind of things. And passive and active technology, I think, very, very important idea. And this sound may be a little bit philosophical, so that I'd like to add some further small explanation on the passive and active technology. Passive technology, yacht is one of the representation of the passive technology. In yacht, they use wind, okay? But motorboat, supposing that I'm on the boat and I'm operating the motorboat, and the wind coming from the front, and then I would imagine that this wind should stop, right? Because I would waste the fossil fuel to move on. But in yacht, we can use that wind to go this way. Well, not directly this way, but with the this, we may move like this and move like this. So we can make a very smart use of the wind blowing around you. So the idea is quite different, passive and active. And the building is the same. We need to think about the use of solar radiation for lighting, heating, and also smart use of the wind coming into the room through windows, and maybe clear story window of the center of, for example, in this room, this building, and so on. And also make use of the heat storage capacity of the concrete wall or maybe soil, that kind of things. So that is originally, the idea comes from the passive technology. So I'm not saying that all of the active technology is wrong, but active technology should be used much more smartly than right now and before. That is something that I like you young people to think about and start some research, or maybe in the future, within 10 years or something, new, I would say, business or maybe technology development and so on. Okay, so this is the summary of what I just mentioned in the first 25 minutes or so. So the problem we face is passive technologies are easily thrown away over the last maybe 50 years or something. And active technology have become too gigantic, as we experienced 3 years ago. So 2 problems to be solved. External environmental problem. That is what now many people are concerned about. Global environment, global warming, and so on. But I think that it is also very important to have some look at the internal environment. I mean, internal, not only meaning the indoor environment, but also internal environment within our body. Why? Later I will show you some very small example how our internal environment works. Okay? And of course, people say that we are facing the energy problem, energy issue. And strictly speaking, for those who have learned some clue on the physics, energy is the concept that is conserved, so not consumed. We cannot consume energy. People say we consume energy, and energy consumption should be minimized. Energy conservation usually means that we use less energy, but in physics, energy conservation is that energy cannot be created, energy cannot be destroyed. We can change from one form of energy into another, but we cannot destroy. That is the concept of energy. So why we can consume energy? That is a very fundamental question that we have to ask and answer. And Exergy is the concept that we can answer in that very simple and very fundamental question. And as I already mentioned in the very beginning, I have been involved in the research on Exergy itself and how to apply the concept of Exergy to describe the human body in the thermal physiology and also the built environment. So I have been involved in such research and also education for many years, and my conclusion so far, and probably will not change in the next 20 years or something, I believe, that is, it is again necessary to have the advanced renewed passive technology. As I mentioned before, passive technology was thrown away very easily. But the very fundamental condition of the built environment should be made with the passive, rational passive technology. That is what we have found through Xsg research. And I will show you why I say so with some chart later. And based on this finding, if we look around the contemporary active technology, air conditioning unit, electric lighting, and so on, all those technologies have not been designed very well so that those technology suit to passive technology. So it's missing. So I'd like you all, if you are very much interested in, just join the technology development that can come up with active technology that is very smart, suiting to passive technology that we really need for the built environment. So, as I already said, human being, our body, the surrounding environment, built environment, and we look at all those things as thermodynamic systems. So the time is quite limited, so that I'd like to show some example. Why human body is important to look at when we talk about the built environment and global environment. We usually, generally speaking, whenever we talk about the energy problem, why don't we reduce the energy use in the air conditioning unit, electric lighting, and so on? But we usually just miss considering the human body, how it works. Okay? So this is example of biological clock. This is not my measurement, but almost 50 years ago, one American physiologist made a very careful observation of a baby, okay? One baby. So this is 24 hours of one day, okay? So you can see line like this. So this is the period of baby sleeping, okay? And blank area, it means they are awake. So just look at the whole chart. You can see, well, this is 25th weeks from his or her birth. So they sleep during nighttime. They wake up around 6 to 8, and they are doing something during daytime, and again start to sleep 8 or 10 o'clock. So basically the same as we do, okay? So, but back in the first, 10 weeks or so, you cannot see this pattern. But still, we see some pattern like this, okay? So this is not the random. There is some pattern, okay? So what is this? So I looked it up in the Rikanenpyo. You know Rikanenpyo, the science data book. And we can see the tide in the Tokyo Bay, when is high and when is low, okay? So the tide is affected by the movement, the Earth, and rotation of the moon relative to the sun. Three things. So with time, 24 hours, this is basically based on the relationship between the sun and the earth, so that whenever something related to the moon, it will shift like this. So high, the rise, fall, rise, and fall. So twice, 2 rises and 2 falls every day. And the exact time is shifted from one day to another. And the 29 days or something, it recover the same pattern, okay? So this is 1 month. Here in this chart, 1 month is here. So let me shrink this. So the pattern looks quite similar, okay? So it is very important to know what it means, okay? So everybody get birth after 10 months in the mother's body, okay? Right after the birth, we cannot see everything. Still, we need 3 months or so to be able to see everything. But still, we have the body clock. Why? Because gravitation affects the human body. And, we come up with the body clock like this. After the birth, taking 6 months, we change the body clock on the basis of the body clock within the mother's body, just like the daytime body clock. So this is why we have something like this, as we all do. So windows of the buildings. Why we have windows? Well, this is very, very important to have the right body clock. Okay? Without windows, if you turn on the electric light, whenever you like, your body clock may vary. But daylight always come into the room every day, even on the day like today, snowy day. So we are not conscious at all, but our body clock synchronizes with the daylight. Okay? So this is the very fundamental of the why windows are necessary. So light is coming in. So it is not smart to make use of the electric lighting in the perimeter zones of the rooms. So well, I'm not criticizing the this university, but the design of the switchboard should be designed so that we can make a full use of the daylighting in the perimeter zone, right? So such a small idea may change the whole human life, okay? So that is one thing that I'd like to mention today very much. So the similar things can be mentioned in terms of the thermal physiology, why we sweat in wintertime, summertime, and why we shiver when we feel too cold, and so on. So let me turn into some other aspect. Again, the human body. This time, I'd like you to raise your hand, okay? A very small question. This is the sun. You all know that the sun gives a great amount of light and heat as you experience in sunny day, right? So we can calculate the amount of light coming off from the sun. And we can also calculate the total mass of the sun. So we can calculate the number A. This is the density of the light and heat coming off from the sun. And we do the same for human body, each of you, okay? And let us make it B. And let us compare A and B, which is bigger or maybe equal, okay? I will give you 3 choices. Mathematically speaking, there are only 3 choices, right? So raise your hand. Number 1, such a density, of course, the sun is bigger. That is number 1, okay? The density, the same, the sun and human body. Number 3, totally different, opposite. Human is bigger. So which one is the right answer? Raise your hand. This is just a quiz, okay? So number 1. Okay. 4, 5. Number 2, the same. So number 3. Okay. So such a dumb or maybe funny question usually gives the funny answer would be right. Okay? So this is the right answer. But surprising thing is how much bigger? Okay? Well, 10 times still too big, you may imagine. But right answer is like this. 10,000 times bigger. We are talking about the density, okay? Not the whole amount, but still very, very curious and sounds a little bit strange. So the sun is so huge, okay? So the relative surface area is very, very small, and the gravitational force is so big That's why fusion takes place inside the sun. In our body, no fusion, only chemical reaction, but very, very complex. So we need such density. Otherwise, we cannot see, we cannot think, we cannot talk, and so on. Okay? So we need to thank all such density of the heat emission. Otherwise, our body will collapse. Okay? So the reason why I say this kind of thing is that this is very important for all of us, the human body, to dissipate the heat produced inside the body to maintain our human body temperature at 37 degrees C. Why 37 degrees C? Because brain works in the right way in that temperature. Stomach works at that temperature, and so on. Okay? So a little bit higher than 37 degrees C, you will get sick. That's why we feel hot. And lower than 37 degrees C, again, you may get sick. That's why you feel cold. So it's very important to maintain our body temperature at 37 degrees C. In doing so, there are only 4 paths, okay? As we measured with this thermometer, radiation. So controlling the radiation is very important. As we notice the window surface temperature, 15 degrees C, like this. So we are losing quite a lot from window and also maybe floor surface. So radiation coming off from our body go into the surface of the floor surface and also window. We have now the drape like this so that we don't feel much coolness from the window, but we still lose some amount of heat by radiation. And convection, you know, the movement of air. And conduction, just feel touch the surface of the desk, and also maybe steel bar like this. This must be felt quite cold, though probably the temperature must be 23 degrees C or something. Please just touch here. (23.9 degrees C), and you feel cool, right? But almost 24 degrees C. So it's still cold. Why? Because a lot of heat go into the steel rather than wood. That's why you feel cold. So if you put the thermally insulating material, that means something like this, onto the surface of the walls, then you can reduce the radiation loss. Then you can make it smaller of the fossil fuel use for the heating of the whole buildings and also electricity use and so on. So all those things are connected each other. And also with the thermal comfort within the human body. So let's move on to the other one, radiation, convection, conduction, and evaporation. I'm sweating a little bit because of my giving a talk, but not many of you might not sweat for this room. But anyway, only those 4 paths are being made for the heat transfer from the human body to the environment. So we have been looking at all such human thermal physiological process with the concept of exergy that I mentioned in the very beginning of this lecture. And in terms of the exergy, Eckert gave a nice introductory talk to you, but I will make a small, brief explanation why exergy is necessary with a series of slides here. Well, it's not possible for me to explain all the things in the concept of exergy within 10 minutes or something, but at least why it is necessary, I hope that I can give you some image. Okay, supposing that there are two tanks. One is 20 liter and the other 5 liter, so 1/4. And in the very beginning, the water temperature is 20 degrees C, both. So we raise the temperature. In this larger tank, we raise the temperature from 20 degrees C to 40 degrees C. So we can calculate how much of thermal energy is contained in this tank after being raised the temperature from 20 to 40 degrees C. So that is 1,674 kilojoules, okay? And we do the same for this smaller tank. And the result is the same. Why? Because the volume is 1/4, but the temperature difference is 4 times larger in this case. In this case, temperature difference is 20, and this case, temperature difference is 80, so 4 times larger. So thermal energy contained by these tanks are the same. And then please imagine that your right hand goes into the bigger tank, okay? It is just like bathing your body in the bathtub, 40 degrees C. Imagine, do the same in the lower tank. What would happen? If I put these two tanks here and ask one of you come in front and do it, then I'll be kicked out from this campus, okay? So you burn, right? Why? The energy is the same. So there is no energy issue, right? Something is missing. So that's why exergy is necessary. And I have to skip how to calculate exergy. And if you are become interested in that kind of things, please ask me later, or maybe Eckart. I can introduce you some textbooks or maybe some introductory paper on the core of the exergy concept. So the result is, in this case, only 55 kilojoule, and in this case, 194 kilojoule. So almost 3.5 times larger in this smaller tank because of the high temperature. Because of the larger exergy, this water has an ability to make some phenomenon, just like burning of the hand. So exergy is the rational concept to show something like this. And another example that we can know of is that raising the temperature, we can do this kind of experiment. Not just making use of the electric heater or gas heater or something. Just put some wheel inside water and turn it around. And this is what James Prescott Joule did in 1850 or something, almost 150 years ago. you know the unit joule. Joule is the rational unit for energy. This is thanks to Mr. Joule, who did a very, very nice experiment 150 years ago. So having some weight like this, raising like this, and if it falls, it has the kinetic energy, but it is the same in terms of exergy. So in the very beginning, weight has the 1,674 kilojoules as potential exergy, which is exactly the same as potential energy, which is the same as thermal energy in this case, okay? So just let this weight fall down to the bottom. So the wheel turns, and the temperature increase from 20 degrees C to 100. So this warm water, the amount of exergy we have is 194. So much smaller than this one. So what happened? This is the exergy balance that we usually call. What happened in respect of exergy is that originally this weight has the potential of exergy 1,674, and let it fall. It means exergy input was made into this water. So the water on the wheel surface, there is the friction like this. You can imagine how it goes. Just put your two hands like this firmly and do like this. You feel hot, right? So this is the friction. And thermal energy dispersed into the water. So in that way, exergy is consumed. And finally, we get this amount. So we call it consumption. This is what we call consumption. And the energy issue is the exergy issue. And why we say energy is consumed and the energy consumption should be reduced. In fact, it means that exergy is consumed and exergy should be reduced. The exergy consumption should be reduced. So we have been looking at how electric lighting works, how the space heating works, how the space cooling in summer works, and so on, and also together with the human body works. And our conclusion is that any systems, not only mechanical system, but also organic systems, human body, the green plant, whatever, any systems work by consuming a portion of exergy that they feed on. Why we eat food? Because we are hungry. But why we are hungry? Because we need some food which contains exergy. Hungry means we would like to have some food. It means, from the viewpoint of thermodynamics, we need exergy. Okay? So any system works by consuming a portion of exergy that they feed on. And consumption is necessary. But as I mentioned, exergy consumption should be reduced. But we need to consume exergy. So exergy consumption can be summarized as the sum of necessary consumption and unnecessary consumption. So unnecessary consumption should be reduced, minimized, or hopefully zero. But we cannot get rid of the necessary consumption. So, for example, in this room, the window, this is not double pane, single pane. And it seems to me that there is no thermal barrier for the concrete clump, so that the much of the heat is lost. So if we put double glazed window and some nice thermal insulation barrier, then exergy flowing out must be minimized. That is the reduction of the unnecessary consumption. Okay? So there are many, many things like that, not only this campus, but also all over Japan, all over the world. So it is very important for you to have a nice eyeglasses that you can see that is the waste, that is the necessary consumption, and so on, and have some rational idea to implement the right technology. Okay? So when is the end? 20 minutes? 20 minutes left? 10 minutes. 10 minutes, okay. Maybe some questions, so I will stop my talk within 7 or 8 minutes, okay? So again, exergy consumption is necessary, and the exergy consumption is the sum of necessary consumption and unnecessary consumption. And unnecessary consumption should be reduced. So I like to show you how the human body consumes exergy in relation to thermal environment. Today is one day of the winter, so that I'll show you some example, especially in winter. This is the one chart showing the exergy consumption rate of the human body varies with the mean radiant temperature, air temperature, and so on. You must not familiar with the technical term mean radiant temperature. It is not so difficult. As I showed you this thermometer, we measure the surface temperature. Well, now, at that time, yes, 23.7 degrees C. Now, it is 25. So in this 1 hour or so, the temperature increased from 23.7 to 25, almost 2 degrees C, right? 1.5 degrees C or something. Why? Because air heating is always heating this room. So air temperature becomes higher and higher, and warm air goes up. So there are some warm air up here. And still, probably floor temperature is 21. So of course, a little bit increased from this, but still low. So anyway, as I demonstrated, we can measure the surface temperature like this. And the horizontal axis shows the average surface temperature. Measure the surface temperature of the ceiling, window, wall, floor, and just make the average. Okay? So 10 degrees C, probably just imagine that this room, no heating at all on a day like this. And air temperature, 14, 18, 22, 24. 4 cases are assumed in this chart. So if the surface temperature is very low and air temperature is very low, this exergy consumption rate of the human body becomes very big. And still, I don't think that you can easily grasp what the exergy consumption rate means, but just imagine that this exergy consumption rate represents thermal stress to the human body. So if the value goes up, it means thermal stress is very big. So thermal stress you should reduce, right? So we need to have the higher surface temperature on average. But if the surface temperature on average goes higher than 25 degrees C, again, thermal stress start to become larger. So in this chart, the minimum Xsg consumption rate occurs just between 22 to 24, something like that. And if you can make the average surface temperature around 22 degrees C or something, it doesn't matter whether you have air temperature at 24 or 22 or 18 degrees C. It doesn't matter. But here in this room, air is being heated. So this is not a rational way of heating. The best way to heat this room is just put thermal insulation, as I mentioned, with something like this, to raise the surface temperature, and just let the air not heated. Even without heating, the air temperature becomes probably 20 degrees C or something, because we human is the large heat source, as we checked in the quiz. Okay? So in this way, with the concept of Exergy, we can know quite a lot of these things. And we also have some similar analysis on the summer, and we can see that the solar control over the window is quite important and so on. And I'm not going to discuss about the summer case today, but let me summarize what is important for winter built environmental conditioning, and then I will stop my talk. So in buildings, appropriate thermal insulation together with the appropriate heat capacity. Heat capacity is the capacity, ability of the materials to store thermal energy, to keep the temperature in a certain period of time in the future. So if you have the nice window setting, and then let the solar radiation transmit into the room, and then if you have some nice wall or floors with thermal capacity, then some part of the solar radiation is stored within the wall and floor and so on. And if you have such thermal insulation material outside the walls, then you can keep warmness during wintertime. And the same applies to the summertime, although solar radiation should be cut with the window surface, but using the nice ventilation during nighttime and so on during summertime, we can store the coolness nicely. So in terms of the solar energy use, many people focus on the use of PV cell, photovoltaic. Of course, it is important, but with solar radiation, we can make use of that as a thermal application. It's very, very important. And many people still do not know how solar radiation in the thermal application should be done. And in terms of the buildings like this, and also homes that you are living in, most of the energy use goes into the application of thermal heat. in winter, space heating, and the whole year you need shower, the dish washing, all those things are heat and cooking, and electricity, TV, refrigerator, and so on. Of course, all those things are necessary, but the whole energy use, 100%, and probably only 20% or something must be electricity. And most of the rest, nearly 80%, is thermal purpose. So it is very important for us to take a look at how thermal insulation works, how solar controlling works, and so on, to have the occupants, we ourselves, live in healthy condition with much comfort, without sacrificing the fossil fuel and so on. And just in time, I think. So I would like to conclude my talk. Thank you very much for your attention.